The illusory nature of reality. A quantum prelude. What if the world we experience, everything we see, touch, hear, and feel, isn't as real as it seems? In the world of quantum mechanics, reality reveals itself as a series of profound mysteries, suggesting that the very fabric of existence may not be as solid and reliable as we believe. In fact, at the smallest scales of existence, particles don't behave like tiny billiard balls bouncing predictably, but act more like waves of possibilities, existing in multiple states at once until observed. Imagine looking at a table, solid and steady, seemingly made of tangible matter. Yet at the quantum level, it's mostly empty space, with particles that can't truly be pinned down to one specific location. Electrons whiz around the nucleus of each atom, not in fixed orbits, but in regions of probability. We call these electron clouds, where the electron could be in several locations at once until it's observed, a concept known as superposition. This leads us to one of the most famous principles in quantum mechanics, the observer effect. When we observe quantum particles, we influence their state. In other words, reality behaves differently when we're watching. The double-slit experiment is a perfect example. When particles like electrons are fired through two slits, they behave like waves, creating an interference pattern as though they're passing through both slits simultaneously. But the moment we try to observe which slit each electron goes through, the pattern changes, and they behave like particles. This experiment suggests that our active observation collapses the wave of possibilities into one specific reality. What does this mean for our perception of the world? Are our senses simply tuned to a particular version of reality, one of many possible configurations? The strange behaviors of quantum particles hint that reality may be a flexible concept, one that depends on observation, perspective, and perhaps even consciousness. The quantum world shows us that the foundations of reality are not as sturdy as they appear. Instead, they're built on a mysterious tapestry of probabilities, relationships, and unknowns, where what we perceive may only be a shadow of a deeper, more intricate truth hidden from our immediate senses. The world as we know it might be a hologram of sorts, a constructed illusion resting on a foundation far more complex than it appears at first glance. Quantum entanglement, the invisible threads of reality. Among the many strange phenomena in quantum mechanics, quantum entanglement stands out as one of the most mind-bending. Imagine two particles that are entangled, meaning they are mysteriously connected no matter how far apart they are. When two particles become entangled, their properties, such as spin, position, or polarization, are linked in such a way that the state of one particle instantaneously determines the state of the other, even if they're separated by vast distances. This phenomenon defies classical understanding, suggesting that information can be transmitted faster than the speed of light. Or perhaps that space itself is not what it seems. Albert Einstein famously referred to this as spooky action at a distance, because it appeared to break the fundamental rule that nothing, not even information, can travel faster than light. Yet, numerous experiments have confirmed the reality of entanglement. In the 1960s, physicist John Bell formulated Bell's theorem, which provided a way to test whether entangled particles really violate classical physics. Through experiments conducted in later years, it was shown that particles do indeed exhibit non-local connections that defy explanation under classical models of reality. In the quantum realm, entanglement suggests that particles are interconnected in ways that transcend physical space, as if they exist on a hidden level where space and time are not obstacles. This connection doesn't convey information in the traditional sense. Rather, it reveals that reality might operate on an invisible network of interdependencies, where everything is fundamentally linked. Some scientists believe this entanglement could be a sign that the fabric of reality is more like a hologram, with information stored across a two-dimensional plane that gives the illusion of three-dimensional space. If our reality is holographic, then every particle and every point in space might be encoded with information that connects it to every other point in space, binding the universe together in a seamless, interconnected web. This concept of universal connectivity has led some to wonder if consciousness itself could be entangled with reality. If particles are connected beyond the limits of time and space, could our own consciousness play a role in shaping what we observe, much like the observer effect in quantum experiments? Some interpretations of quantum mechanics propose that the universe only chooses a specific outcome when a conscious observer is involved, implying that reality is inextricably linked to our awareness of it. Quantum entanglement challenges us to reconsider our understanding of space, time, and separateness, hinting that reality is far more fluid and interconnected than it appears. It suggests that distance, as we perceive it, may simply be an illusion, and that each particle, each atom, is woven into a larger, indivisible fabric of existence, a reality where nothing truly stands alone. The quantum observer. Does reality depend on consciousness? One of the most profound questions raised by quantum mechanics is whether consciousness itself plays a role in shaping reality. The idea that an observer influences what is observed may sound like science fiction, but it's an inherent feature of the quantum world. At the smallest scales, particles do not appear to have definite states or positions until they are observed. Instead, they exist in a superposition, a combination of all possible states at once, until the act of observation causes this probability wave to collapse, giving the particle a specific position or state. This mysterious role of the observer is best illustrated by the double-slit experiment, where particles like electrons behave like waves when no one is watching, creating interference patterns as if they pass through both slits at once. However, when an observer measures which slit each electron passes through, the interference pattern disappears, and the electrons behave like particles, as though they have chosen a single path. This raises a baffling question. Does the very act of observing force particles to decide on a definite state? Some physicists have interpreted this phenomenon to mean that reality, at least at the quantum level, requires a conscious observer to take form. This interpretation is often associated with the Copenhagen interpretation of quantum mechanics, proposed by physicist Niels Bohr in the 1920s. Bohr suggested that particles exist in a state of potential, not actual existence, until observed. In other words, reality as we experience it could be shaped by the very act of looking at it. The idea that consciousness might be fundamental to reality has inspired theories that stretch beyond traditional physics. Could it be that consciousness itself is a fundamental aspect of the universe, interwoven with the very fabric of existence? Some interpretations even suggest that consciousness and quantum phenomena are interconnected in ways we're only beginning to understand. This notion has fascinated not only physicists but also philosophers, who wonder if the universe behaves like a cosmic theater, unfolding in response to an audience of observers. Interestingly, this notion has parallels in ancient philosophical traditions. In certain Eastern philosophies, the concept of Maya describes the world as an illusion, shaped by perception and awareness. This idea resonates with the quantum principle that reality is not fixed until it's observed. Just as quantum particles appear to decide their state in response to observation, so too do these philosophies suggest that our reality is, in part, a construct of the mind. While this interpretation remains one of many, it underscores a deep and tantalizing question about the nature of reality. If our consciousness shapes the reality we experience, then to what extent is the world we see a product of our perception, rather than an independent, fixed entity? The quantum observer effect challenges our most basic assumptions, suggesting that reality may not be a separate, objective world out there, but a dynamic construct, responding to and even shaped by our consciousness itself. Parallel realities and the many worlds interpretation. The possibility of multiple realities existing side by side may seem like the stuff of science fiction, but quantum mechanics presents a compelling argument for the existence of parallel worlds. This concept, known as the many worlds interpretation, was first proposed in 1957 by physicist Hugh Everett. In this interpretation, every quantum event, the collapse of every probability wave into a specific state, does not result in a single outcome, but rather in all possible outcomes, each unfolding in its own distinct universe. Imagine a simple decision, such as flipping a coin. In a classical view, the coin lands on either heads or tails, resulting in one fixed reality. But in the many worlds interpretation, the universe splits, creating two parallel versions, one where the coin lands on heads and another where it lands on tails. This concept applies to every quantum event, from the movement of an electron to more complex systems like human decisions. In each case, a new reality branches off, forming a countless number of alternate worlds where every possible outcome plays out. If true, this theory implies that an infinite number of realities are constantly emerging, each with its own version of events, individuals, and histories. It suggests that there may be versions of ourselves living entirely different lives in worlds that are only a quantum fluctuation away. Some of these alternate universes might be nearly identical to our own, while others could be dramatically different, shaped by a single change in a quantum outcome billions of years ago. While the many worlds interpretation remains speculative, there is indirect support for the idea in quantum mechanics. For instance, the behavior of particles in superposition can be explained as the result of a multitude of worlds where each possible position or state of the particle is realized. The theory also bypasses the need for a conscious observer to collapse the wave function, as each outcome exists in its own branch of reality. In this view, the universe is a constantly branching tree of possibilities, with new realities budding off with every quantum event. The implications of this interpretation are staggering. It suggests that our reality is only one of an unimaginably vast number of parallel worlds. These worlds might be inaccessible to us, but they are as real as our own, coexisting in a vast, invisible multiverse. If this interpretation holds, the boundaries of what we consider real expand dramatically, challenging our assumptions about existence and individuality. In the many worlds interpretation, reality is not a singular linear path, but a boundless multiverse of infinite pathways, each shaped by quantum events and choices. This perspective doesn't just add mystery to the universe. It redefines what it means to live in a reality where every possibility, no matter how improbable, might indeed be unfolding right now in a parallel dimension, just beyond our perception. Quantum superposition, living in a state of possibilities. One of the most intriguing phenomena in quantum mechanics is the concept of superposition, the idea that particles can exist in multiple states or positions at once, only choosing a specific state when observed. To imagine this, think of Schrödinger's famous thought experiment. A cat placed in a sealed box with a mechanism that has a 50% chance of killing it, triggered by the decay of a radioactive atom. Until the box is opened and we observe the cat, it is both alive and dead simultaneously, existing in a superposition of states. In the quantum world, superposition applies not just to theoretical cats, but to particles like electrons, photons, and even larger molecules. Quantum particles aren't confined to a single location or state. They are spread out across a range of possibilities. These particles act more like waves of probability, creating interference patterns that represent multiple potential positions or states. This concept is so central to quantum mechanics that it defies our common sense, challenging the classical notion that an object exists in a single state at any given moment. Quantum superposition is not limited to abstract thought experiments. Scientists have demonstrated superposition in laboratory settings, where particles display wave-like behavior when unobserved, allowing them to pass through multiple states or paths. In experiments where particles like photons or electrons are fired through a pair of slits, they create interference patterns that suggest they have traveled through both slits at once. This behavior vanishes when an attempt is made to measure their path, collapsing the superposition into a single outcome. This aspect of quantum mechanics opens up a profound question. If particles can exist in multiple states, what does this mean for reality at larger scales? Could it be that our own reality exists in a superposition of possibilities, and that what we experience as solid and fixed is merely a choice from a field of potentialities? The quantum world suggests that the universe is not as deterministic as we once thought. Rather, it is fluid and flexible, with each moment holding a range of possibilities, waiting to unfold based on conditions and observations. Some interpretations even propose that our consciousness may exist in a similar superposition, where we live within overlapping realities and interact with only one version at a time. This is a challenging concept, yet it aligns with theories that see consciousness as non-local, potentially interacting with the quantum field itself. From this perspective, the experience of life may be a continual collapsing of possibilities, where each choice we make or experience we observe pulls one thread of reality into being, leaving the other possible outcomes as unrealized potentials. Quantum superposition challenges our understanding of existence, suggesting that what we perceive as a stable, singular reality might be one outcome among many, a fleeting arrangement in a universe of limitless possibilities. Each observation, each choice, may narrow down the field, yet beneath this surface of chosen realities lies an infinite canvas of potential paths, where perhaps every possibility exists, and reality as we know it is only one version of a deeply layered, infinitely branching tapestry. The uncertainty principle, embracing the limits of knowledge. In the quest to understand reality, quantum mechanics introduced one of its most famous and perplexing principles, the uncertainty principle. Formulated by Werner Heisenberg in the 1920s, this principle reveals an inherent limitation to what we can know about particles on the quantum scale. Specifically, the uncertainty principle states that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This is not due to flaws in measurement technology, but a fundamental feature of the quantum realm itself. To grasp this, imagine trying to pinpoint an electron's exact location and its speed simultaneously. On a classical level, measuring both would be straightforward, like clocking the position and speed of a car on the highway. But in the quantum world, such measurements disrupt the system, creating a ripple in the delicate quantum fabric. Attempting to observe a particle's precise position causes its momentum to blur, while measuring its momentum makes its position uncertain. This duality isn't just a quirk of physics. It suggests that at the most fundamental level, reality may have a built-in ambiguity. The uncertainty principle forces us to confront a universe that defies complete knowledge, introducing a threshold to what we can know about the underlying details of any quantum system. Even particles like protons and electrons don't behave as isolated, trackable entities, but are instead bound within a cloud of probabilities, where exact knowledge is perpetually out of reach. This isn't to say particles don't exist in a real sense, but rather that their properties are interwoven in a way that prevents any single measurement from capturing their full essence. Heisenberg's principle has sweeping implications for how we understand reality. It suggests that on a fundamental level, the universe isn't governed by deterministic laws, but by probabilities. Particles don't follow rigid paths. They follow likelihoods, existing in a realm where the future is open to multiple possible outcomes. This lack of certainty challenges the classical Newtonian view of a clockwork universe, where everything unfolds in a predictable way. The uncertainty principle extends beyond particles, too, affecting systems at increasingly large scales. Some scientists even suggest that our perceptions, decisions, and consciousness itself could be influenced by this intrinsic uncertainty. In everyday life, we may experience this principle as an intangible feeling that our understanding of reality is always, in some way, incomplete. Could it be that uncertainty, rather than being a flaw or a limitation, is an essential part of existence? A built-in feature that gives rise to creativity, spontaneity, and the unknown? Interestingly, the uncertainty principle also gives rise to the concept of quantum fluctuations, tiny, spontaneous changes in energy that happen in the so-called quantum vacuum, a state once thought to be entirely empty. But the quantum vacuum isn't void. It teems with fleeting particles popping into and out of existence, constantly shifting in response to the inherent uncertainties in energy and position. These fluctuations are so powerful that they are thought to have driven the initial rapid expansion of the universe in the Big Bang. The uncertainty principle teaches us that reality isn't a fixed, orderly framework, but rather a shifting landscape where probabilities and possibilities coexist. It compels us to accept the unknown as an integral part of existence, inviting us to embrace mystery and ambiguity. This principle hints at a universe that resists full comprehension, suggesting that at the deepest levels, reality holds secrets that may forever elude us. A realm where knowledge itself is limited not by our technology, but by the very nature of the universe. Quantum field theory. Reality as a vibrating field of energy. In the realm of quantum mechanics, particles like electrons, photons, and quarks are not seen as independent solid objects, but as excitations or ripples in vast energy fields that fill the entire universe. This perspective comes from quantum field theory, QFT, a framework that views reality as an intricate network of interacting fields, each with its own unique characteristics and energy levels. When we think of a particle, we're actually observing a localized vibration within one of these fields, a ripple of energy manifesting briefly before returning to the field from which it came. Imagine the quantum fields as the surface of a pond. A raindrop hitting the pond creates ripples that spread outward, altering the surface momentarily. In QFT, particles are like these ripples, only instead of water, they ripple through fields of energy that extend through all of space. An electron is simply an excitation of the electron field. A photon is a ripple in the electromagnetic field, and so on. These fields are everywhere, even in regions we perceive as empty space, giving rise to a concept that challenges the very idea of nothingness. This perspective not only redefines particles, but also suggests that the essence of reality is more fluid and interconnected than we previously imagined. Fields overlap, interact, and influence each other continuously. The Higgs field, for example, permeates all of space, and it's through interactions with this field that certain particles acquire mass. Discovered in 2012 at the Large Hadron Collider, the Higgs boson is often referred to as the particle that gives mass, but it's really a ripple in the Higgs field, highlighting that mass itself isn't an intrinsic property of particles, but a feature that arises from their relationship with this field. Quantum field theory also sheds light on the concept of virtual particles, ephemeral excitations that pop in and out of existence within the quantum vacuum. These virtual particles constantly fluctuate due to the inherent uncertainties in energy, creating a sort of energetic sea within empty space. This quantum vacuum, far from being devoid of activity, buzzes with the energy of countless fleeting particles that influence even stable, observable particles through what's called vacuum polarization. What does this mean for our understanding of reality? If all particles are simply excitations in their respective fields, then reality, at its core, is composed not of individual isolated objects, but of interconnected energy patterns. We, too, are essentially temporary ripples in the quantum fields, assembled in a specific complex pattern that we recognize as ourselves. Our senses may interpret this world as solid and unchanging, but at the quantum level, we're in constant flux, vibrating with the fields that define existence itself. Quantum field theory reveals a picture of reality as a vast, dynamic system of energy, where what we perceive as separate objects are simply expressions of deeper, unifying fields. This challenges the idea of individuality, hinting that all forms and phenomena are connected at a foundational level, united by the interplay of these fundamental fields. In this framework, the concept of reality as an illusion becomes clearer. Solid matter dissolves into patterns of energy, woven together by the invisible but omnipresent threads of quantum fields. Quantum foam, the bizarre landscape of space-time itself. At the smallest scales of the universe, space-time itself becomes a wild, chaotic landscape known as quantum foam. Proposed by physicist John Wheeler, quantum foam is the idea that space-time, far from being smooth and continuous, is in fact granular, fluctuating, and teeming with random bursts of energy at scales close to the Planck length. The smallest scale of the universe, far tinier than atoms or subatomic particles. At these infinitesimal dimensions, space-time appears to be bubbling with constant activity, with particles popping in and out of existence and gravity behaving in ways that defy classical understanding. This foamy structure of space-time means that our perception of a smooth, continuous reality is, in some ways, an illusion. At the quantum scale, space is not empty but filled with unpredictable fluctuations in energy, creating tiny, temporary wormholes and bizarre, fleeting structures. These fluctuations are so intense that the very geometry of space can twist and fold in unpredictable ways, allowing particles to momentarily borrow energy from the vacuum before vanishing once again. This phenomenon is a consequence of the Heisenberg uncertainty principle applied to space-time itself. In these regions, energy and duration of existence are in a constant, fluctuating dance. Quantum foam has major implications for our understanding of gravity. In our everyday lives, gravity seems predictable and constant, shaping the orbits of planets and the flow of time. But at the quantum level, the strength of gravity fluctuates wildly with these bubbles of energy. This unpredictability makes it difficult to unify gravity with the other fundamental forces in a single framework, as these fluctuations resist the smooth equations of classical theories. Some theorists even speculate that quantum foam could serve as a substrate for wormholes, tiny passages through space-time that could, theoretically, link distant points in space. In this view, the fabric of the universe may be more interconnected than it appears, with minute shortcuts between locations in space hidden within these microscopic folds of space-time. Quantum foam reveals a reality that defies our traditional concepts of emptiness and solidity, where even space-time itself exists in a state of constant change. If this is the true nature of reality, then everything we perceive, from solid objects to the vastness of space, is built upon an underlying tapestry of randomness and impermanence. Our everyday world, with its sense of continuity and stability, might be merely a veneer over a universe in flux, constantly bubbling with the energy of creation and annihilation, a quantum illusion crafted from the ever-shifting landscape of space-time foam. Quantum consciousness, the mystery of mind and matter. In exploring the nature of reality, a tantalizing question emerges. Could consciousness itself be connected to the strange properties of the quantum world? While the relationship between mind and matter remains one of science's greatest mysteries, some physicists and philosophers have proposed that consciousness might not be a mere byproduct of brain activity, but a phenomenon influenced by, or even rooted in, quantum processes. One such theory, called quantum consciousness, suggests that our thoughts, perceptions, and awareness could be shaped by quantum mechanics at the level of microtubules within brain neurons. Proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, this idea posits that quantum processes might operate within the tiny structures inside neurons, affecting the flow of information and potentially linking consciousness to quantum states. This approach, while still speculative and controversial, raises the possibility that consciousness could involve entanglement or superposition within the brain. If consciousness operates on a quantum level, then awareness itself might experience effects akin to quantum phenomena. Consider the concept of superposition. Just as particles can exist in multiple states simultaneously, could our consciousness also operate on multiple levels of awareness at once, choosing only one state as our focus at any given moment? In this view, reality could be an interaction between external information and a quantum-based mind that collapses possibilities into the specific perceptions we experience. Additionally, the concept of entanglement might provide a clue to the interconnected nature of thought and experience. Entangled particles remain connected regardless of distance, suggesting a potential model for telepathy or collective consciousness, where minds might be linked on a quantum level, sharing information across distances. This idea is, of course, hypothetical, but it hints at the profound ways that quantum principles could interact with the subjective experience of mind. The observer effect in quantum mechanics also plays into questions of consciousness. If observing a particle causes it to choose a specific state, does our consciousness play a similar role in shaping reality? Could it be that what we perceive as an independent reality is partially constructed by our minds, a reflection of our focused awareness interacting with the underlying quantum field? This line of thought resonates with age-old philosophical questions about perception and reality, reminiscent of Descartes' "I think, therefore I am," suggesting that awareness could be a powerful factor in creating the world we experience. While no scientific consensus exists on quantum consciousness, the idea bridges quantum mechanics with philosophical inquiries into the nature of mind and existence. It suggests that consciousness might not merely be an emergent phenomenon arising from classical physical processes, but a fundamental aspect of the universe, deeply embedded in the fabric of quantum reality. If true, this could mean that our experience of self and the outer world are intricately connected, two sides of a quantum coin. Quantum consciousness challenges the boundaries of what it means to be aware, alive, and connected to the universe. It hints that our minds could be much more than biological machines, suggesting instead that we might be active participants in an interconnected, quantum-driven reality. A reality where consciousness and the cosmos are intertwined in ways we are only beginning to understand. The holographic principle. Is reality a projection? The holographic principle is a radical idea that has captured the imagination of physicists and philosophers alike, suggesting that our three-dimensional reality might be a projection from a two-dimensional surface. At the heart of this theory is the notion that the entire universe could be like a hologram, where all the information about what we perceive as a three-dimensional world is encoded on a two-dimensional boundary. The origins of the holographic principle trace back to research on black holes. In the 1970s, physicist Jacob Bekenstein proposed that the amount of information, or entropy, that can be stored in a black hole is proportional not to its volume, but to the area of its event horizon, the boundary surrounding the black hole. This finding, later expanded by Stephen Hawking, showed that a black hole's entropy could be described by the surface area around it, not the space within it, challenging our classical intuitions about volume and information. In the 1990s, physicist Leonard Susskind and Nobel laureate Gerard T. Hooft proposed that this concept could apply to the entire universe, not just black holes. According to the holographic principle, the information describing every particle, every field, and every bit of energy in our three-dimensional universe could be stored on a distant two-dimensional surface, potentially at the boundary of the universe itself. In this view, what we experience as depth or volume might be an illusion, a projected construct similar to a hologram, which appears three-dimensional despite being encoded on a flat surface. But how does this holographic view fit with quantum mechanics and relativity? One important connection lies in the study of quantum gravity, which seeks to reconcile quantum mechanics with Einstein's theory of relativity. In this pursuit, theoretical models have suggested that the holographic principle could explain how space-time and gravity emerge from quantum information on this two-dimensional boundary. This perspective hints that what we perceive as space, time, and gravity might arise from deeper, more fundamental interactions that occur on a flat, informational boundary. The holographic principle also aligns intriguingly with findings from string theory, a theoretical framework that describes particles as tiny, vibrating strings. In some models, string theory supports the idea that our universe might be a lower dimensional slice of a higher dimensional reality. If true, this would imply that our perceived world is but a shadow or projection of a deeper, more complex dimension, an idea that has been explored in everything from theoretical physics to philosophy. What does this mean for our understanding of reality? If the universe is a hologram, then everything we see, from stars to atoms, could be the projection of underlying information on a distant boundary. In this view, our perception of depth, solidity, and separateness would be like the images on a holographic film, real in experience, but ultimately encoded on a flat surface. The holographic principle not only challenges our perception of reality, but also suggests that our individual experiences may be projections within a shared, larger reality, connected through a fundamental informational structure. It implies that existence itself is a network of information, and that we, along with everything around us, are expressions of this cosmic code. In such a universe, reality may not be what it seems, and our sense of separation from the cosmos might be an illusion, as we're all connected by a vast, invisible web of information on the surface of reality itself. Time and quantum reality. Is time an illusion? Time is one of the most mysterious aspects of reality. We experience it as a continuous flow, moving from past to future in a linear progression. Yet quantum mechanics and theories of relativity offer perspectives that challenge this intuitive view. Could it be that time, as we perceive it, is merely an illusion? Einstein's theory of relativity introduced a revolutionary idea. Time is not an absolute, universal experience, but a flexible dimension, intricately woven with space. The faster we move, the slower time passes relative to someone at rest, a phenomenon called time dilation. In extreme conditions, such as near a black hole, this effect becomes profound, with time stretching almost to a standstill relative to distant observers. This bending of time suggests that our linear experience of past, present, future might be a limited perspective rather than a fundamental feature of the universe. Quantum mechanics adds further mystery. At the quantum scale, particles don't appear to experience time in the same way we do. Quantum entanglement, for instance, seems to act instantaneously, with entangled particles affecting one another without regard for distance or the passage of time, as if connected outside the constraints of temporal flow. If entanglement operates beyond time, could this mean that time itself is not a foundational aspect of reality? One interpretation that seeks to explain these quantum oddities is the block universe model. According to this theory, all points in time, past, present, and future, exist simultaneously within a four-dimensional block. In this view, time doesn't flow. Rather, every moment in time is like a frame on a film reel, fixed and unchanging, with the illusion of passage created by our consciousness moving through these frames. This means that the future may already exist, with each moment simply unfolding in our perception. We experience a sense of flow, but it might only be the mind's way of processing existence. In the quantum realm, the ambiguity of time becomes even stranger. Experiments suggest that particles don't necessarily follow a linear sequence of events. In quantum processes, effects sometimes appear to occur before their causes, with particles seemingly influenced by future conditions in a phenomenon called retrocausality. In these cases, the future seems to reach back to influence the present, further eroding the classical view of time as a strict forward march. This suggests that at a fundamental level, time might not dictate the sequence of events as rigidly as we experience in our day-to-day lives. The concept of time as an illusion has also been explored in various philosophical traditions, particularly in Eastern philosophies that view time as cyclical or as an illusion crafted by human perception. According to these perspectives, time is not an objective reality, but a construct of consciousness, a way for the human mind to order experiences. Quantum mechanics and relativity seem to echo this view, suggesting that time may be less like a river and more like a landscape, where all events exist concurrently, and our perception is what moves. If time is indeed an illusion or a construct of perception, it challenges the very core of our understanding of reality. It implies that concepts like before and after might be artifacts of human experience rather than universal truths. In this framework, reality could be a timeless fabric, with all events and possibilities existing together in an eternal now, giving us a glimpse into a universe where time, as we know it, is a shadow of a more complex, timeless reality. In considering time as an illusion, we come closer to understanding the quantum reality where past, present, and future might not be separate entities, but facets of a single, interconnected whole. And if this is true, then our lives, our choices, and our very existence might transcend the passage of time, placing us in a universe where every moment is both fleeting and eternal. Quantum immortality, the survival of consciousness across universes. The concept of quantum immortality presents a provocative idea. In a universe governed by quantum mechanics and the many worlds interpretation, consciousness might never truly experience death. According to this view, whenever an event occurs that could lead to an observer's death, there exists at least one alternate reality in which they survive. Consequently, a conscious observer might only experience realities in which they continue to exist, effectively creating a version of immortality across multiple universes. Imagine a scenario where an individual faces a life-or-death situation, such as a dangerous accident. In one branch of the multiverse, the individual might not survive, while in another parallel reality, they do. From the perspective of the observer's consciousness, they would continue in the version where they survive, as they wouldn't be able to experience a version in which they cease to exist. This idea, often referred to as quantum suicide, forms a thought experiment that has sparked philosophical debates on consciousness, mortality, and the nature of identity. While speculative, quantum immortality suggests that consciousness might be inherently linked to the many worlds interpretation. If each quantum event creates new branches of reality, and if consciousness can persist only in branches where it continues to exist, then in a sense, each observer might experience an unbroken chain of survival across countless parallel universes. This doesn't imply traditional immortality. Rather, it implies that consciousness could hop across realities in which it remains alive, facing new circumstances but never reaching a definitive end. This concept challenges our understanding of death and identity, suggesting that consciousness itself might be a kind of quantum wave that exists across a vast array of realities. From this perspective, death in one universe wouldn't prevent the persistence of consciousness in another. The notion aligns intriguingly with the idea that reality is a branching tree of possibilities, where each branch represents a unique version of events and outcomes. Quantum immortality also raises questions about the nature of self-awareness. If we exist across multiple universes, does our consciousness remain linked only to the reality we perceive? Or could it imply that consciousness operates non-locally, extending across multiple branches simultaneously? Some interpretations propose that consciousness might exist as a form of quantum entanglement, connected to various versions of ourselves in parallel realities. While no empirical evidence currently supports quantum immortality, it stretches our conception of life and death in fascinating ways. If true, the phenomenon would suggest that what we perceive as an end might simply be a transition, a narrowing down of possible experiences rather than a final curtain. It hints that our awareness might be part of a larger interconnected web of possibilities, flowing from one existence to another. In the landscape of quantum reality, quantum immortality is a thought-provoking perspective that challenges our most fundamental beliefs about existence. It proposes a universe where consciousness might be an unending journey through a multiverse of experiences, offering a glimpse into a reality where life and death are not absolutes, but shifting states within a cosmic tapestry of endless possibilities. The simulation hypothesis. Is reality a programmed illusion? The simulation hypothesis proposes a radical idea that everything we experience, from the laws of physics to our sense of self, could be part of a highly advanced simulation. Popularized by philosopher Nick Bostrom in 2003, the hypothesis suggests that if technology continues to advance, a civilization could eventually create simulations so detailed that the simulated beings would have conscious experiences indistinguishable from reality. At the heart of the hypothesis lies the idea that, just as we create virtual environments in video games or simulations, future civilizations could develop technology capable of simulating entire universes. Given enough computing power, the simulated beings within these universes might become self-aware, developing consciousness and identities, all while existing in a fabricated reality. If such advanced civilizations exist, it's statistically plausible that the number of simulated realities could vastly outnumber base reality, meaning that any conscious being would be more likely to inhabit a simulation than an actual physical universe. Quantum mechanics adds a fascinating layer to this hypothesis. The observer effect and the probabilistic nature of quantum particles could be explained as aspects of a simulation optimized for processing efficiency. In this view, particles only decide their state when observed to conserve computing resources, much like how video game environments only render fully when they come into a player's view. The simulation hypothesis provides a potential explanation for the unpredictable, probabilistic behaviors in quantum mechanics, suggesting that these phenomena might be signs of the underlying code. This idea also raises the possibility that the fundamental constants of the universe, like the speed of light or Planck's constant, could be parameters set by the programmers of this simulated reality. If reality is a simulation, then the seeming laws of nature may be more like rules in a complex code, fine-tuned to create a coherent, stable universe. Of course, the simulation hypothesis is speculative, and it's impossible to prove or disprove from within the simulation itself. However, it challenges us to consider the nature of reality from a completely different angle. If we are indeed in a simulation, then the world as we know it might not be the final level of existence, but a creation within a higher, perhaps inconceivably advanced civilization. The simulation hypothesis raises profound philosophical questions about existence, consciousness, and purpose. It suggests that our reality could be an intricate illusion crafted by unknown forces, making us active participants in an elaborate, programmed universe. A cosmic game where the boundaries of reality are set by lines of code rather than the forces of nature. The role of perception, constructing reality through the mind. Our perception of reality is not simply a direct experience of the world around us. Rather, it's an intricate construction pieced together by our senses, brain, and mind. Every moment, our brain processes an enormous amount of sensory data, from the photons hitting our eyes to the vibrations entering our ears, filtering and interpreting these signals into a cohesive picture of reality. Yet, this construction isn't flawless. It's selective, biased, and influenced by our personal experiences, beliefs, and biological limitations. In many ways, our perception is a custom-built illusion shaped to make sense of the world. Consider color. While we see the sky as blue and grass as green, colors are not inherent properties of objects, but experiences created by the brain. When light reflects off an object, it enters the eye, where it's processed by cone cells sensitive to different wavelengths. The brain then interprets this data and assigns colors. But without our perception, color wouldn't exist as we know it. It's an experience generated in the mind, not an external reality. This principle applies to many aspects of perception. Sounds are merely air vibrations until interpreted as meaningful information by our auditory system, just as temperature is a subjective sensation rather than an absolute property. Perception doesn't just process reality, it actively constructs it. Psychologists refer to this phenomenon as perceptual filtering, a process that allows us to focus on certain details while ignoring others. Without this, we would be overwhelmed by sensory input, unable to make sense of our surroundings. The subjective nature of perception aligns intriguingly with certain ideas in quantum mechanics. In the quantum realm, particles exist in multiple states until they are observed, collapsing into a definite state only upon measurement. Similarly, our brains create a collapsed version of reality, discarding other possible interpretations to deliver a singular, coherent experience. This raises the question, is the world we experience a true reflection of reality, or merely one interpretation among many? Philosophical traditions have long suggested that our senses limit our understanding of reality. Plato's allegory of the cave, for instance, describes prisoners who see shadows on a wall and believe them to be the entirety of existence. This allegory serves as a reminder that our senses may only provide a limited, filtered version of the true nature of reality. Modern neuroscience supports this idea, showing that the brain's interpretations are often more symbolic than literal. For example, optical illusions reveal how easily our perceptions can be deceived, showing us that what we see isn't always what's out there. Studies on perception demonstrate that each individual constructs reality in a unique way, shaped by their brain's interpretations, which are influenced by everything from past experiences to cultural expectations. In many ways, perception is a bridge between mind and reality, a lens through which we interpret the quantum world of possibilities in the material world we navigate. By understanding that our view of reality is, in essence, a construct, we come closer to appreciating the fluid and potentially illusory nature of existence. Our perception is not a passive receiver of truth, but an active creator of the world we experience, an illusion born of interpretation and shaped by the mind. The nature of consciousness, an enigma beyond matter. Consciousness remains one of the greatest mysteries in science and philosophy. While we understand the physical processes that support life, how neurons fire, how blood circulates, and how senses function, the experience of being aware, of having an inner self, defies straightforward explanation. Where does consciousness come from, and how does it connect to the physical universe? Some theories suggest that consciousness is an emergent property of complex neural networks, while others propose that it may be fundamental to the fabric of reality itself, challenging us to redefine what we consider real. Traditionally, consciousness has been studied as a byproduct of brain activity, a phenomenon emerging from the countless interactions among billions of neurons. Neuroscientists explore how brain regions work together to create awareness. And though we have mapped cognitive functions to brain structures, this approach has yet to explain the subjective experience of consciousness. This is often referred to as the hard problem of consciousness, a term coined by philosopher David Chalmers to highlight the difficulty in understanding why and how subjective experiences, or qualia, arise from physical processes. One intriguing theory is panpsychism, which posits that consciousness is a fundamental feature of the universe, similar to space, time, and energy. According to this view, everything in existence, from atoms to stars, possesses some form of consciousness or mind, albeit at vastly different levels. In panpsychism, consciousness doesn't emerge from complexity but exists inherently, meaning that even the smallest particles contain a basic form of awareness, which may combine to form the richer experiences we associate with human consciousness. While controversial, panpsychism bridges the gap between physical matter and conscious experience by suggesting that mind-like qualities permeate the universe. Another perspective, known as the Integrated Information Theory, IIT, suggests that consciousness is directly linked to the amount of information that can be processed and integrated by a system. The more complex and interconnected a system, the higher its level of consciousness. This theory provides a potential explanation for why human beings, with highly interconnected brains, experience rich, complex consciousness, while simpler organisms have a more limited experience. IIT proposes that consciousness is an intrinsic aspect of any system capable of integrating information, hinting that awareness might exist in various forms throughout the universe. The enigma deepens when we consider quantum mechanics. Some interpretations, such as the orchestrated objective reduction model, propose that consciousness arises from quantum processes within brain microtubules. Here, consciousness isn't just a byproduct of neural activity, but may be fundamentally quantum, tied to the probabilistic nature of particles. This idea, though still hypothetical, opens up the possibility that consciousness operates on a level intertwined with quantum phenomena, resonating with theories that suggest reality itself is influenced by the observer. These diverse theories push the boundaries of what we know about consciousness, inviting us to explore it as potentially more than a byproduct of the physical. If consciousness is woven into the universe's fabric, it could mean that our sense of individuality, of being separate from the cosmos, is an illusion. Consciousness might be an expression of the universe perceiving itself, making each of us a unique perspective within a vast, interconnected consciousness field. Whether we view it as an emergent property of the brain or as a fundamental component of reality, consciousness challenges the conventional division between mind and matter. It suggests that reality, as we perceive it, might be shaped by the very awareness through which we observe it. In this way, consciousness could be both the observer and the observed, a force that creates and defines reality itself, a mystery beyond matter, yet intrinsically bound to it. Non-locality and the interconnected universe. In the vast world of quantum mechanics, the principle of non-locality reveals a fascinating truth. Particles can influence each other instantaneously across any distance, as though the fabric of space and time doesn't constrain them. This phenomenon was first observed in the 1960s through Bell's theorem, which provided a way to test the spooky action at a distance predicted by quantum entanglement. Experiments have since confirmed that entangled particles remain connected no matter how far apart they are, challenging our conventional understanding of separateness and locality. Non-locality suggests that particles that have once interacted retain a connection that allows them to respond to changes in each other's state instantaneously. If one particle's spin is measured, its entangled partner instantly assumes a complementary spin, regardless of distance. This instant connection hints that the universe might operate on a deeper level where all things are fundamentally interconnected, and separateness is an illusion crafted by our limited perspective. This principle doesn't only apply to subatomic particles. It invites questions about the interconnectedness of larger systems, perhaps even human beings or consciousness itself. In fact, non-locality has inspired various theories about how consciousness might tap into a shared, universal network, allowing minds to connect in ways that traditional physics can't explain. For instance, concepts like telepathy, intuition, or the sensation of oneness with the universe might be reflections of this quantum interconnection. Non-locality also provides a new lens through which to view space and time. Classical physics assumes that objects interact through forces that travel across space over time. But if non-locality is a fundamental property, then space itself may be less of an absolute entity and more of a construct that organizes experiences. Theories like quantum gravity and holography even suggest that space could emerge from entanglement patterns within the quantum field, hinting that distance is not an inherent feature but a product of quantum relationships. In light of this, reality might be a web of interactions, a network where each point is connected to every other, revealing a holistic view of existence. Instead of thinking of objects as isolated entities, we might imagine them as nodes in a universal field, where every point in the universe is intrinsically linked to every other. In this way, our lives, our experiences, and even our minds may be part of an interconnected system, one where the boundaries between self and cosmos dissolve. What's more, non-locality challenges the notion that consciousness is restricted to individual minds. If all particles are interconnected at a fundamental level, then consciousness too might be a shared experience across space and time, woven into the very structure of the universe. This hints at the idea that our sense of individuality could be one facet of a greater, unified consciousness that spans the cosmos, with each of us acting as unique expressions of a single, interconnected whole. Non-locality opens the door to a more expansive view of reality, one where everything is connected, not merely in a metaphorical sense, but in a literal, quantum physical sense. It suggests that reality, as we experience it, is a deeply connected network, with separateness as the illusion and unity as the underlying truth. In a non-local universe, boundaries dissolve, reminding us that every part of reality, seen and unseen, is interwoven into a single shared existence. The role of the observer, shaping reality through observation. In the quantum realm, the observer plays an unexpectedly central role in shaping reality. This concept is known as the observer effect, where the act of observation appears to alter the state of particles. Before a particle is observed, it exists as a probability wave, with no definite position, momentum, or state. But once observed, this wave collapses, and the particle chooses a specific state, as if the observer's presence brings it into tangible existence. This phenomenon is demonstrated in the famous double-slit experiment, where particles such as electrons or photons pass through two slits to create an interference pattern on a screen, behaving as waves that interfere with themselves. However, if an observer measures which slit the particles pass through, the interference pattern disappears, and they behave as particles, traveling through one slit or the other. This shift in behavior suggests that observation doesn't merely record reality, it actively influences it. The observer effect raises profound questions about the nature of consciousness and its relationship with the material world. Could our awareness, our act of looking, be essential to the way reality unfolds? Some interpretations of quantum mechanics, such as the Copenhagen interpretation, propose that observation is fundamental, collapsing probabilities into specific outcomes. This implies that, at least on a quantum level, reality might be indeterminate until it interacts with consciousness. In addition to individual consciousness, the observer effect invites questions about collective observation. Does the shared observation of billions of minds stabilize reality, creating a more consistent and solid universe? Philosophers and scientists alike have pondered whether consciousness acts as a kind of glue that holds reality together, enabling a cohesive experience out of a quantum sea of possibilities. This notion resonates with ancient philosophical ideas that consciousness and reality are intimately connected. In Hinduism, for instance, the concept of Maya suggests that reality is an illusion shaped by perception. Similarly, in Buddhism, the perception of separateness and permanence is seen as a mental construct. These perspectives echo the observer effect, suggesting that what we consider real is, in part, a reflection of our awareness, a world shaped and stabilized by the act of observing. The observer effect challenges our deepest assumptions about an objective, independent reality. It hints that reality could be a co-creation, emerging from the interaction between consciousness and the quantum field. This interconnected dance between observer and observed suggests that reality is not a fixed stage upon which events unfold, but a dynamic, interactive phenomenon, continuously shaped by the awareness that experiences it. The quantum void, the paradox of empty space. What we consider empty space might be far from empty. In the quantum world, even a perfect vacuum, devoid of atoms or particles, is filled with an underlying structure called the quantum vacuum, or quantum void. This void is a paradox, as it appears empty but is, in reality, teeming with potential, with particles constantly appearing and disappearing in fleeting bursts of existence. This seemingly empty space is alive with virtual particles that pop into and out of existence, lending a dynamic and mysterious quality to the very concept of nothingness. The energy in this vacuum is the basis for what physicists call quantum fluctuations, minute changes in energy that occur spontaneously. These fluctuations are unpredictable and are allowed by the Heisenberg uncertainty principle, which states that there is a limit to how precisely we can know a particle's energy and the time it exists. Because of this uncertainty, particles can borrow energy from the vacuum for brief moments, creating pairs of particles and antiparticles that annihilate each other almost instantaneously. One of the most mind-bending consequences of this vacuum energy is the Casimir effect. In this phenomenon, two uncharged parallel plates placed very close together in a vacuum will experience an attractive force toward each other due to quantum fluctuations. These fluctuations create a difference in the energy density between the plates and the surrounding vacuum, effectively pushing the plates together. This surprising force, which arises from the energy of empty space itself, demonstrates that the quantum vacuum is anything but empty. It's a reservoir of energy that can have real, measurable effects. The quantum void also hints at the possibility of vacuum energy or zero-point energy, the lowest possible energy that a quantum mechanical system can have, even in the absence of particles. Some theories suggest that if this energy could be harnessed, it might offer near-limitless power, though doing so remains far beyond our current technological capabilities. The implications are profound, as the quantum vacuum could be a hidden source of energy permeating the universe, a fundamental aspect of the cosmos that we have only begun to understand. Exploring the nature of empty space has also led to theoretical breakthroughs in understanding the origins of the universe. Some models of cosmology propose that the Big Bang could have emerged from a quantum fluctuation within the vacuum. In this view, the universe itself might be a manifestation of the quantum void, where a fluctuation in the vacuum created the conditions necessary for space-time, matter, and energy to arise. The quantum void reveals that what we perceive as nothing is an illusion. The so-called emptiness of space is a veil over an active, dynamic quantum field that holds the seeds of existence. This invisible energy, present everywhere, hints at a universe where creation is continuous, where every point in space is alive with the potential for matter, energy, and even new universes. In the quantum realm, even nothing is something, a fertile ground for the mysteries and paradoxes of existence. Quantum biology, the unseen influence of quantum mechanics on life. Quantum mechanics, once thought to operate only within the microscopic world of atoms and particles, has shown intriguing signs of influencing biological processes as well. This emerging field, known as quantum biology, explores how the strange rules of the quantum realm could play a crucial role in the mechanics of life. From photosynthesis in plants to navigation in birds, quantum effects are increasingly suspected to underpin some of the most complex biological systems. One of the most studied examples of quantum biology is photosynthesis. Plants, algae, and certain bacteria rely on photosynthesis to convert sunlight into chemical energy. This process begins when photons, particles of light, are absorbed by chlorophyll molecules in plant cells, transferring energy to electrons. Recent studies suggest that this energy transfer occurs through a phenomenon called quantum coherence, where electrons can exist in multiple states simultaneously, allowing them to explore multiple paths and find the most efficient route to the plant's reaction center. This efficiency, nearly 100%, would be impossible without the advantages offered by quantum coherence, where energy navigates multiple possible paths at once before choosing the most direct route. Another fascinating example is found in the magnetic sense of migratory birds. Birds like the European robin use Earth's magnetic field to navigate during their long migrations. Research suggests that this magnetic sense could be based on a quantum process in a protein called cryptochrome, located in their eyes. When light excites the cryptochrome molecule, it creates entangled electron pairs that are sensitive to magnetic fields. This entanglement helps birds perceive the direction of Earth's magnetic field, a form of biological quantum compass that might allow them to sense their direction without conscious effort. Quantum mechanics is also thought to play a role in the process of olfaction, or the sense of smell. Traditional theories propose that scent molecules bind to receptors in the nose based on their shape. However, experiments have shown that the vibrational frequency of molecules may be a factor in how they're detected. Some scientists believe that scent detection could involve quantum tunneling, where electrons jump across gaps between molecules in the nose in response to specific vibrational frequencies. This would mean that our sense of smell might rely on quantum mechanics, detecting not just the shape, but also the quantum vibrations of molecules. In the realm of genetics, quantum mechanics may even be involved in mutations at the DNA level. Quantum tunneling could allow protons to shift positions within DNA molecules, causing spontaneous changes that can lead to mutations. While some of these mutations are harmless, others could drive evolution, potentially influencing the direction of life over long timescales. If quantum processes contribute to genetic variability, then quantum mechanics might play a hidden role in the way life adapts and evolves on Earth. Quantum biology hints that life itself may depend on quantum processes, operating at levels we are only beginning to understand. Rather than being confined to physics experiments and particle behavior, quantum mechanics could be an essential component of biological systems, enabling life to achieve efficiency and adaptability in ways that would otherwise be impossible. These processes challenge the classical notion of biology as merely a chemical and molecular science, opening a door to a new understanding of life as a phenomenon intertwined with the quantum world. If quantum effects influence life, then the boundary between biology and physics blurs, suggesting that the fundamental rules of quantum mechanics might be as integral to life as they are to the cosmos. It implies that living beings, from the simplest bacteria to the most complex organisms, may be deeply connected to the quantum fabric of reality, guided by principles that transcend traditional biological explanations. Quantum biology expands our understanding of life, reminding us that the mysteries of existence are as much within us as they are in the distant stars. Quantum paradoxes, the strange limits of reality. The quantum world is filled with paradoxes, phenomena that defy common sense and challenge the boundaries of reality as we understand it. These paradoxes force us to confront the limitations of our perception and reveal the deep strangeness underlying the fabric of existence. From Schrödinger's famous cat experiment to the peculiarities of wave-particle duality, quantum paradoxes hint that reality may be far stranger than we could have ever imagined. One of the most well-known paradoxes is Schrödinger's cat, a thought experiment that illustrates the bizarre implications of superposition. Imagine a cat placed in a box with a vial of poison that's released based on the decay of a radioactive atom. Until someone opens the box to observe, quantum mechanics suggests the cat is in a superposition of both alive and dead states simultaneously. Only upon observation does the wave function collapse, forcing the cat into one state or the other. This paradox challenges the notion of an objective reality, suggesting that states of existence may depend on the presence of an observer. Another striking paradox in quantum mechanics is the concept of wave-particle duality. Particles like electrons and photons exhibit both particle-like and wave-like properties depending on the experimental setup. In the double-slit experiment, particles fired through two slits create an interference pattern on a screen, behaving like waves that pass through both slits simultaneously. Yet, when detectors are placed to observe which slit each particle travels through, the interference pattern disappears, and the particles behave as though they only pass through one slit. This paradox defies classical intuition, implying that reality's behavior changes depending on our approach to observing it. The quantum Zeno paradox is another counterintuitive phenomenon. This paradox suggests that a particle's decay or quantum state can be frozen by observing it frequently enough. Named after the Greek philosopher Zeno, this paradox implies that constant observation can prevent a quantum system from evolving, a phenomenon likened to a watched pot never boiling. This observation-dependent behavior challenges the classical notion that reality unfolds independently of the observer, suggesting instead that observation itself may have a physical effect on time and change. Quantum entanglement presents its own paradox. When particles become entangled, they share properties that are instantaneously connected, regardless of distance. Changing the state of one particle immediately influences the other, an effect that appears to operate faster than light, defying classical physics. This spooky action at a distance puzzled even Einstein, who struggled to accept the idea of a universe where particles could be instantaneously connected in ways that transcend the limitations of space-time. These paradoxes force us to reconsider our fundamental understanding of reality, challenging assumptions of determinism, locality, and objectivity. They hint at a universe that does not follow rigid, predictable rules, but is instead guided by probabilities, observation-dependent states, and connections beyond the constraints of time and space. In this view, reality may be as much a product of our interaction with it as it is an independent phenomenon. Quantum paradoxes reveal the limits of human intuition and suggest that reality might not be graspable through classical understanding alone. They remind us that reality's true nature may exist beyond our current frameworks, and that the mysteries of existence may forever challenge the boundaries of our knowledge and perception. Quantum tunneling, passing through the barriers of reality. Quantum tunneling is a phenomenon that defies classical logic, allowing particles to pass through barriers that should be impenetrable. According to classical physics, if a particle lacks the energy to overcome a barrier, it should simply bounce back. However, in the quantum world, particles have a probability of tunneling through such obstacles, appearing on the other side as if the barrier was never there. This phenomenon defies our everyday experiences and demonstrates the curious ways in which the quantum world operates. To understand quantum tunneling, imagine a hill and a ball that doesn't have enough energy to roll over it. Classically, the ball would always fall back. In quantum mechanics, however, the ball has a certain probability of appearing on the other side of the hill, effectively passing through it. This behavior stems from the particle's wave-like nature, allowing it to spread out and exist as a probability wave that extends through and beyond the barrier. When the particle decides its position, there is a small chance it will manifest on the other side. Quantum tunneling is essential to many natural processes. For instance, It plays a critical role in nuclear fusion within stars, where hydrogen nuclei overcome the repulsive force between them and fuse together to form helium, releasing vast amounts of energy. Without tunneling, the conditions required for fusion would be unattainable in most stars, making this strange quantum effect fundamental to the creation of the elements and the energy produced by stars. Quantum tunneling also has implications in modern technology. In semiconductors, for example, tunneling allows electrons to pass through tiny gaps in electronic components, enabling the operation of transistors in devices like smartphones and computers. The phenomenon is even harnessed in scanning tunneling microscopes, which use tunneling electrons to image surfaces at an atomic scale, revealing details invisible to traditional microscopes. Beyond its practical applications, tunneling challenges our understanding of space and barriers. It suggests that in the quantum realm, the concept of boundaries is far less rigid than in the classical world. Particles are not confined in the ways we assume. They can exist in places we wouldn't expect, transcending the boundaries of what seems physically possible. Quantum tunneling offers a glimpse into a reality where boundaries and limitations are more fluid than we perceive. It reminds us that what we consider impossible in our macroscopic world may be entirely plausible on the quantum scale, where the rules of reality stretch beyond the limits of classical intuition. Quantum decoherence, the collapse of possibility into reality. Quantum decoherence provides a potential explanation for why we don't observe the strange behaviors of quantum particles, like superposition, in our everyday lives. In the microscopic world, particles can exist in multiple states at once, creating interference patterns and other strange phenomena. But in the macroscopic world, the world of tables, chairs, and planets, this superposition vanishes. Decoherence explores how interactions with the environment cause quantum systems to collapse into a single state, creating the stable reality we experience. To understand decoherence, imagine an electron existing in a superposition of multiple locations simultaneously. Left undisturbed, it can maintain this ambiguous state. However, the moment the electron interacts with other particles or becomes entangled with its surroundings, these multiple states become incompatible with one another. The environment measures the electron, causing it to lose its superposition and adopt a definite state. This process is not the same as direct observation by a human. Rather, it is the natural interaction with the surroundings that forces a particle to settle on a single outcome. Decoherence is essential to explaining why the quantum world seems so strange and disconnected from our everyday experience. In the quantum realm, everything is inherently uncertain and exists in a cloud of probabilities. But as soon as a quantum system becomes entangled with the environment, it appears to collapse into a specific state, masking the underlying superposition and creating the illusion of a solid, singular reality. Interestingly, decoherence has led to various interpretations of quantum mechanics, including the many worlds interpretation. In this view, decoherence doesn't cause a single outcome, but rather splits the universe into multiple branches, with each possible outcome realized in a parallel universe. When a particle's state decoheres, it doesn't vanish. Rather, it continues to exist in an alternate reality where that outcome is the chosen state. Thus, decoherence doesn't truly destroy possibilities, but rather divides them across an infinitely branching multiverse. Decoherence also helps explain the stability of classical objects, like why a book stays on a table and doesn't suddenly teleport elsewhere. These macroscopic objects are constantly interacting with countless particles in the environment, making any quantum superposition so fragile that they collapse almost instantly. This constant measurement by the environment ensures that objects maintain stable positions and defined properties, reinforcing the sense of a reliable, predictable world. In practical terms, understanding decoherence has implications for fields like quantum computing. Quantum computers rely on maintaining superpositions in quantum bits, or qubits, to perform computations that would be impossible with classical computers. However, these qubits are extremely sensitive to environmental interactions, making decoherence a major obstacle in building stable, functional quantum computers. Engineers must isolate qubits from external disturbances to prevent decoherence and retain their quantum states. Quantum decoherence serves as a bridge between the probabilistic, ambiguous quantum world and the stable, predictable reality we experience. It highlights how the universe is not made up of isolated, discrete objects, but rather of systems constantly interacting and influencing one another. Through decoherence, the strange behaviors of particles collapse into the tangible reality we know, shaping a universe that seems continuous, yet is woven from probabilities that dissolve the moment they're touched by the world around them. The anthropic principle. A universe fine-tuned for observation. The anthropic principle suggests that the universe's physical constants, the laws of nature, and its very structure appear to be fine-tuned to allow for the existence of observers like us. While there are many possible universes with varying properties and physical laws, only a narrow range would permit the formation of galaxies, stars, planets, and life. The anthropic principle raises the question: is the universe structured this way by coincidence, or does it exist specifically to enable conscious observers? One example of this fine-tuning is the force of gravity. If gravity were even slightly weaker, stars might not form, and without stars, the elements essential for life, carbon, oxygen, nitrogen, would never have been synthesized. If gravity were stronger, stars would burn through their fuel far too quickly for complex life to evolve. Similar fine-tuning appears in other constants, like the strength of the electromagnetic force, the ratio of the electron to the proton mass, and the rate of cosmic expansion, all of which lie within very narrow ranges that support life. There are two main versions of the anthropic principle: the weak anthropic principle and the strong anthropic principle. The weak anthropic principle simply states that we observe the universe as it is because only in such a universe could observers exist in the first place. In other words, the universe has to have the properties it does for us to be here to observe it. Any other configuration would not support life, so we wouldn't be around to question it. The strong anthropic principle, however, goes further. It suggests that the universe not only permits life, but is structured in a way that almost seems to anticipate it. According to this view, the emergence of conscious observers is not a mere byproduct of cosmic processes, but a fundamental feature of the universe. This idea hints at a deeper connection between the cosmos and consciousness, where the universe may be fine-tuned for the purpose of giving rise to life and, ultimately, awareness. The anthropic principle is often debated in relation to the multiverse theory. If our universe is just one of countless others within a multiverse, each with different physical constants, then it's less surprising that at least one universe, ours, has properties that support life. In this case, we could simply be living in a lucky universe among many others that are inhospitable. This interpretation allows for a statistical explanation of fine-tuning, suggesting that life-supporting universes are rare but inevitable across the multiverse. Another perspective explores whether consciousness might play a role in shaping the universe itself. Some interpretations of quantum mechanics, as we've seen, suggest that observation has a fundamental impact on reality. In this light, the anthropic principle raises the possibility that consciousness is not merely a passive byproduct of a structured universe, but an active participant in defining that structure. This line of thinking touches on philosophical questions about existence and purpose, suggesting that consciousness could have a fundamental relationship with the cosmos. The anthropic principle reminds us of the incredible balance present in the universe, a balance that allows for the complexity and diversity we see. Whether this balance is purely coincidental, the result of a multiverse, or evidence of a deeper purpose, the anthropic principle offers a humbling perspective on our place in the cosmos. It suggests that reality, as finely tuned as it is, could be much more than a random collection of particles and forces. It could be an intricate, purpose-filled design that not only allows us to observe, but may in some way be shaped by our very act of observing. The zero-point field. Infinite energy in the quantum vacuum. The zero-point field, often referred to as the ground state of the quantum vacuum, represents a realm of infinite potential. In quantum mechanics, even at absolute zero temperature, where all classical motion ceases, particles retain a residual energy known as zero-point energy. This energy, present in every point of space, arises from the uncertainty in energy and position, creating a persistent, fluctuating field where particles and waves constantly appear and vanish in fleeting virtual forms. The existence of zero-point energy was first suggested in the early 20th century by physicist Max Planck and later expanded by others, including Albert Einstein. It is the lowest possible energy state of a quantum system and is responsible for the spontaneous fluctuations in energy that give rise to virtual particles. These virtual particles, though short-lived, have measurable effects, such as the Casimir effect. This phenomenon occurs when two closely spaced metal plates in a vacuum experience an attractive force due to the difference in zero-point energy outside and between them, providing a tangible demonstration of the energy present in empty space. The zero-point field challenges our understanding of nothingness. Far from being empty, the vacuum is filled with a seething energy field, with virtual particles popping in and out of existence. This has led some physicists to speculate that zero-point energy might one day be harnessed as a near-limitless source of power. If accessible, it could provide humanity with an endless energy source. However, tapping into zero-point energy remains theoretical and would require advanced technology beyond our current capabilities. Some theories suggest that zero-point energy could even play a role in the expansion of the universe. The presence of this energy in every part of space could contribute to what we observe as dark energy, the force responsible for accelerating the expansion of the cosmos. In this view, the quantum vacuum isn't just a background, but an active participant in cosmic evolution, constantly influencing the large-scale structure of the universe. The zero-point field offers a glimpse into a reality where empty space is brimming with potential, a source of energy and influence beyond our direct experience. This hidden field invites us to reconsider the nature of the vacuum and the fundamental structure of reality, reminding us that even in the apparent emptiness of space, there is a reservoir of energy that shapes the universe in unseen, mysterious ways. Quantum gravity, seeking the unification of reality's forces. Quantum gravity represents one of the most ambitious quests in modern physics, uniting the force of gravity, which governs large-scale structures like planets and stars, with quantum mechanics, which describes the microscopic world of particles. Gravity is explained through Einstein's general theory of relativity, where massive objects curve the fabric of space-time, creating the gravitational force. Yet, this classical description breaks down when applied to the tiny scales of quantum particles, where probabilities and superpositions dominate. The goal of quantum gravity is to bridge this gap, creating a unified theory that can explain the behavior of all matter and energy across every scale. One of the leading theories in the pursuit of quantum gravity is string theory. This theory proposes that instead of point-like particles, the basic constituents of the universe are tiny vibrating strings. Each type of particle corresponds to a particular vibration mode of these strings, and in string theory, gravity is represented by a particle called the graviton, a hypothetical particle that mediates the gravitational force in the quantum realm. String theory also suggests the existence of multiple dimensions beyond our familiar three-dimensional space and time, which are curled up in ways that are invisible at our scale. If true, these extra dimensions could fundamentally alter our understanding of reality. Another approach to quantum gravity is loop quantum gravity, which proposes that space-time itself has a discrete, granular structure at the smallest scales, with units known as loops, or spin networks. In this framework, space-time isn't a continuous fabric but a web of interconnected loops, each representing a quantum unit of space. These loops could form the foundation of a quantum description of gravity, suggesting that space-time itself is quantized. Loop quantum gravity aims to reconcile the quantum world with the large-scale structures governed by general relativity without the need for extra dimensions, making it a distinct approach from string theory. A third, emerging approach is based on holography, inspired by the holographic principle. This idea suggests that our three-dimensional universe could be encoded on a two-dimensional surface, similar to how information on a holographic film creates the illusion of depth. In this view, gravity and space-time might emerge from quantum information on this boundary, offering a pathway to unifying gravity with quantum mechanics. Holography has gained attention for its success in describing certain black hole properties, where information on a black hole's event horizon can encapsulate its entire three-dimensional interior. Quantum gravity holds the potential to explain not only the behavior of black holes and the early moments of the universe, but also to provide a framework for understanding everything from the smallest particle interactions to the evolution of galaxies. If achieved, it could reshape our understanding of reality, showing us that space, time, and matter are interwoven in ways that are profoundly different from classical interpretations. In the pursuit of quantum gravity, physicists aim to reveal a deeper layer of reality where the division between the quantum and classical worlds dissolves. It hints that the universe might be more interconnected and dynamic than we've ever imagined, a seamless continuum where gravity and quantum mechanics are facets of a single unified force. The journey toward a theory of quantum gravity may one day redefine our understanding of existence itself, providing a roadmap to the fundamental structure of reality. Quantum weirdness, embracing reality's bizarre foundations. Quantum mechanics challenges not just our understanding of particles and forces, but our intuition about the nature of reality itself. Concepts like superposition, entanglement, and wave-particle duality reveal that the quantum world doesn't operate under the rules we experience in daily life. Instead, it behaves in ways that seem deeply strange and counterintuitive, what many physicists refer to as quantum weirdness. But what if this weirdness isn't a glitch in our understanding, but a window into a reality far richer and more complex than we can imagine? One of the most bizarre aspects of quantum mechanics is the idea that particles can be in multiple places or states simultaneously, known as superposition. In a quantum system, a particle such as an electron doesn't occupy a single location. Instead, it exists as a cloud of probabilities that represents all possible states at once. This cloud only collapses into a single state when observed, a phenomenon that raises questions about the nature of reality when no one is watching. Does the universe choose a definite state only when observed, or is it somehow inherently indefinite? Entanglement adds another layer of mystery to this picture. When particles become entangled, their states become linked so that changes to one particle affect the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, defies the classical idea that objects must interact through direct contact or forces that travel over time. Instead, entanglement suggests that particles remain interconnected in a way that transcends spatial separation, as though they are part of a single, indivisible whole. This behavior challenges the notion that the universe is composed of independent objects, hinting instead at an underlying unity. Then there's wave-particle duality, which defies classical categories altogether. Particles like electrons and photons can behave either as particles or as waves, depending on how we measure them. In the double-slit experiment, particles create an interference pattern, acting as waves when unobserved. But when detectors are used to determine which slit each particle passes through, they behave like discrete particles, as though deciding on their nature based on our interaction. This raises a profound question about the relationship between reality and observation. Does our observation actually influence the behavior of particles, or are particles inherently dual in nature? These strange behaviors aren't limited to isolated experiments. They underpin the entire quantum world. And yet, they seem to contradict our understanding of causality, locality, and objectivity, forcing us to redefine what we consider real. Some interpretations suggest that the quantum world reflects a deeper, hidden layer of reality, where traditional concepts like space and time lose their meaning, replaced by a realm of possibilities and probabilities. The bizarre aspects of quantum mechanics have led to various interpretations, each attempting to explain the universe's strange behavior. The many worlds interpretation, for instance, proposes that every possible outcome exists in a separate, parallel universe. In this view, every quantum event is a branching point where the universe splits into different realities, with each possibility realized in a different world. Another perspective, known as the Copenhagen interpretation, suggests that particles remain in superposition until observed, at which point they choose a definite state. Quantum weirdness forces us to confront a reality that operates outside the constraints of human intuition. It suggests that reality might not be a fixed stage where events play out independently of observation, but an interactive, participatory experience shaped by the act of observation itself. Rather than seeing the world as a predictable machine, quantum mechanics invites us to consider it as an intricate, interconnected dance of probabilities, where particles and observers form a unified system. As strange as it seems, quantum mechanics hints that reality might be fundamentally different from what we perceive. It challenges us to embrace uncertainty, letting go of absolute truths in favor of a universe that is dynamic, fluid, and deeply mysterious. A reality where weirdness is not an exception, but the rule. Quantum reality and the nature of free will. The nature of free will has long fascinated philosophers and scientists alike, but quantum mechanics adds a surprising dimension to this ancient debate. If the quantum world is fundamentally governed by probabilities rather than certainties, what does this imply for free will? Are we merely following predetermined paths shaped by biology and physics? Or does the probabilistic nature of quantum mechanics suggest that we have some degree of freedom in shaping reality? In classical physics, the universe is seen as a deterministic system, a clockwork machine where each cause has a specific effect. In this view, the state of every particle in the universe, including those that make up our brains, determines every future state, implying that free will could be an illusion. But quantum mechanics challenges determinism. The Heisenberg uncertainty principle, for example, introduces limits to what we can know about a particle's position and momentum simultaneously. And quantum systems appear to evolve based on probabilities, not fixed outcomes. Quantum indeterminacy means that certain events cannot be predicted with absolute certainty. They only have a range of possible outcomes. This inherent randomness suggests that the universe is not entirely predetermined, as particles and events may choose among probabilities. This opens the door to a model where free will could, in theory, coexist with physics, as our actions might not be entirely preordained, but instead shaped by the influence of quantum probabilities. Some interpretations even propose that consciousness could play a role in collapsing quantum possibilities. In the Copenhagen interpretation, a system exists in a superposition of states until it's observed, at which point it chooses a particular state. If consciousness is somehow linked to the collapse of the wave function, then the act of making choices could be akin to observing quantum possibilities, with our decisions influencing the path reality takes. This view is speculative, yet it hints at a model where conscious choice could impact the probabilistic landscape of the quantum world. Another intriguing perspective comes from the many worlds interpretation, which suggests that every possible outcome of a quantum event is realized in a parallel universe. If true, this would imply that every choice we make branches into different realities, with each version of ourselves experiencing a different outcome. In one sense, this could mean that free will doesn't involve choosing a single path, but instead exploring all possibilities across an infinite multiverse. Each decision splits reality, creating multiple versions of ourselves, each with its own experiences and outcomes. Ultimately, the question of free will within a quantum framework remains unresolved, but it challenges us to think of choice and action as part of a probabilistic reality. It hints that, rather than following strict laws, our actions might unfold in a landscape of possibilities, influenced but not entirely dictated by prior causes. This probabilistic view leaves room for a reality where, within the boundaries of quantum probabilities, conscious beings may indeed influence the world around them. Quantum mechanics invites us to reconsider free will, not as an absolute, but as a dynamic interplay of choices within a flexible, uncertain universe. Rather than a fixed path, life might be an ongoing interaction between choice and chance, suggesting a reality where we participate actively in the unfolding of events, one where the nature of our existence and the choices we make shape a quantum-driven, ever-branching reality. The nature of nothing. exploring the quantum void and cosmic origins. The concept of nothing has intrigued humanity for millennia, yet in physics, nothingness is far from simple emptiness. At the quantum level, even nothing is something, alive with energy, fluctuations, and the seeds of potential. This quantum void, known as the quantum vacuum, is a field of spontaneous, invisible energy present throughout all space. While the idea of a cosmic void might imply complete absence, quantum mechanics reveals that what we call empty space is, in fact, a dynamic field that plays a vital role in the origins and structure of the universe. Quantum fluctuations, tiny bursts of energy that arise in the vacuum, represent the dynamic character of this void. Even in a state of perfect emptiness, uncertainty in quantum mechanics allows for brief and spontaneous appearances of particles and antiparticles. These particles pop into existence for an instant, borrowing energy from the vacuum before annihilating each other and disappearing. This continual creation and annihilation is a hallmark of quantum nothingness, hinting that even in the void, the universe is far from inactive. These fluctuations are not merely theoretical. In the Casimir effect, two uncharged metal plates placed very close in a vacuum experience a measurable force pulling them together due to differences in vacuum energy between the plates and the surrounding space. This effect demonstrates the tangible impact of quantum fluctuations, showing that the quantum vacuum can exert physical influence on objects in the real world, despite being empty by conventional standards. Exploring nothingness at a cosmic scale raises even bigger questions about the origin of the universe itself. Some cosmological theories suggest that the entire universe may have emerged from a quantum fluctuation in the vacuum. The notion that something could arise from nothing may sound counterintuitive, but quantum mechanics provides a framework in which this could happen. In this view, the Big Bang, the beginning of our universe, could have been a quantum event, a spontaneous fluctuation where energy briefly borrowed from the quantum vacuum expanded rapidly, giving rise to space, time, and everything within it. This perspective challenges classical notions of causality and creation, suggesting that nothing is fertile ground for the birth of entire universes. The quantum vacuum, in this framework, could be a primordial sea of potential, where quantum fluctuations give rise not only to particles, but to the very fabric of space and time. In this way, the vacuum might be more than an empty background. It could be a fundamental component of cosmic evolution, constantly influencing and shaping the universe in unseen ways. Some interpretations even speculate that the universe we inhabit is one of many, each potentially emerging from similar quantum fluctuations. If true, this could imply a multiverse, a vast collection of universes, each with its own unique laws and constants, born from the same fertile nothingness. In this scenario, our universe might be just one outcome among countless others, each the result of a quantum fluctuation within the vacuum. This understanding of the quantum void reveals that what we think of as nothing may hold the ultimate keys to reality. Rather than being a mere absence, it is a source of constant energy, interactions, and possibilities. This perspective redefines our understanding of existence, suggesting that even in the apparent void, there is a structure teeming with activity and potential. The quantum void may be the source of not only matter and energy, but also the space-time framework that governs the universe. In the end, the quantum nature of nothing shows us that the concept of emptiness is, in itself, an illusion. Beneath the silence and stillness of the void, reality is alive with potential, a place where existence and non-existence are woven together. This realization challenges us to rethink our assumptions about the fabric of reality, inviting us to view the universe as a creation emerging from the depths of a vibrant, ever-active nothingness. Quantum fields and the fabric of reality. The notion of quantum fields offers a radical way to view reality, suggesting that particles aren't individual entities but rather disturbances or ripples within fundamental fields that permeate the universe. According to quantum field theory, QFT, every fundamental particle, whether an electron, photon, or quark, is simply a localized excitation of an underlying field that spans all of space. In this view, what we perceive as particles are not isolated objects, but temporary fluctuations in these omnipresent fields. To visualize this, imagine the surface of a pond. When a pebble drops into it, ripples form, spreading across the water. In QFT, each particle is akin to one of these ripples, with the field acting as the pond itself. Just as the pond exists continuously even when undisturbed, these fields are present everywhere, filling even what we think of as empty space. This means that our perception of solid particles is, in fact, a result of the underlying fields interacting, merging, and vibrating across the fabric of space. Quantum field theory emerged in the early 20th century as physicists sought to unify quantum mechanics with the theory of electromagnetism. Today, it stands as one of the most successful models in physics, forming the basis of the Standard Model, a comprehensive framework describing 3 of the 4 known fundamental forces: the electromagnetic, weak, and strong nuclear forces. The Standard Model's accuracy in predicting particle interactions, confirmed through countless experiments, shows how deeply quantum fields govern our universe. One of the most intriguing aspects of quantum fields is the idea of the Higgs field. In 2012, scientists at CERN confirmed the existence of the Higgs boson, the particle associated with the Higgs field, by detecting its unique energy signature. The Higgs field gives certain particles mass, effectively slowing them down and allowing them to interact in complex ways to form atoms and, ultimately, matter as we know it. Without the Higgs field, particles would have no mass, and the universe would be an entirely different place, one without the structure or stability required for stars, planets, and life. Quantum fields are also key to understanding the quantum vacuum. Even in the absence of particles, fields retain an underlying energy, known as zero-point energy. This residual energy, ever present in all fields, suggests that empty space is far from inactive. Instead, it is a seething lattice of fluctuating energy, constantly shifting and interacting at a quantum level. The zero-point energy of these fields could even play a role in phenomena such as dark energy, the mysterious force accelerating the expansion of the universe. Through quantum fields, we glimpse a reality that defies traditional notions of objects, space, and emptiness. Rather than being made of discrete particles, the universe appears to be an interconnected web of fields, constantly vibrating and exchanging energy. In this framework, particles are temporary events within the fields rather than standalone objects, underscoring the fluid, dynamic nature of existence. Quantum fields reveal that reality is a deeply unified and energetic fabric. What we perceive as matter is an expression of these fields interacting in complex, precise ways, creating the illusion of solid, independent objects. As we delve deeper into this quantum reality, we uncover a universe more interconnected and unified than we ever imagined, where even the simplest particle is a ripple on the surface of an unseen, boundless ocean of energy. The quantum potential of consciousness, bridging mind and matter. Could consciousness itself be intertwined with quantum processes? This provocative idea, often called the quantum mind hypothesis, proposes that our thoughts, perceptions, and even our sense of self might operate in ways influenced by quantum mechanics. If consciousness is more than a byproduct of neural activity, it may connect directly to quantum fields or processes within the brain, bridging mind and matter in ways we are only beginning to understand. One prominent theory exploring this idea is known as orchestrated objective reduction, OR, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that quantum processes might occur within microtubules, structures within neurons that are small enough to potentially maintain quantum coherence. According to OR, consciousness could arise when these microtubules reach a threshold of quantum activity, leading to moments of awareness. While speculative, this theory has inspired a growing interest in examining consciousness through a quantum lens, asking whether awareness might be more than a neurological process but a quantum phenomenon. Quantum consciousness theories often explore the idea of non-locality. the concept that particles can be interconnected across vast distances without a direct link. In the context of consciousness, non-locality could imply that our minds are not entirely localized within our brains, but might be connected to a larger collective network of awareness. This line of thinking resonates with concepts like Carl Jung's collective unconscious, suggesting that individual minds could be entangled with a universal consciousness, or even with each other, a phenomenon that some believe could explain experiences like intuition, empathy, or even telepathy. The observer effect in quantum mechanics adds further mystery to the link between consciousness and reality. If observation influences particle behavior at a fundamental level, could consciousness itself play a role in shaping the physical world? This interpretation hints that mind and matter might not be separate entities but interconnected aspects of reality. The famous double-slit experiment reveals that particles behave differently when observed, suggesting that the act of observation itself collapses quantum possibilities into one specific outcome. If consciousness acts as an observer in this context, it may be actively participating in defining reality. Such ideas invite us to consider whether consciousness might exist independently of the brain, perhaps as a fundamental aspect of the universe, similar to gravity or electromagnetism. In this view, consciousness could be a field permeating all things, giving rise to awareness in complex structures like the human brain, but not limited to biological forms. If consciousness is indeed a fundamental part of the universe, it could explain phenomena like near-death experiences, or even the sensation of interconnectedness that mystics describe across cultures. Quantum theories of consciousness remain controversial and speculative, and rigorous scientific evidence is still needed. However, these ideas offer a framework for understanding consciousness as a process deeply embedded in the fabric of reality. They hint that our minds are not isolated within our skulls, but are potentially connected to the larger quantum tapestry of the universe, part of a vast and dynamic interplay between thought, perception, and matter. If true, these theories suggest that consciousness might be more than a fleeting byproduct of brain chemistry. Instead, it could be a fundamental aspect of existence, a bridge between the observable universe and the deeper quantum reality that underpins it. The quest to understand consciousness through quantum mechanics challenges our understanding of life, identity, and reality itself, offering a vision where mind and matter are intertwined in an intricate cosmic dance. The future of quantum technology, harnessing the power of the quantum realm. Quantum technology stands on the edge of revolutionizing fields from computing to communication and even medicine. At the heart of this innovation is the unique ability of quantum systems to exist in multiple states simultaneously, or to entangle particles that remain interconnected across vast distances. These properties, though strange, offer extraordinary potential for creating technology far beyond the limitations of classical mechanics. Quantum computing is perhaps the most well-known application. Unlike classical computers, which process information in binary, ones and zeros, quantum computers utilize qubits, which can exist in a superposition of both states at once. This ability enables quantum computers to perform complex calculations at exponentially faster rates, making them ideally suited for tasks like cryptography, drug discovery, climate modeling, and artificial intelligence. By processing multiple possibilities simultaneously, quantum computers can solve problems that would take classical computers millions of years. Another frontier of quantum technology is quantum cryptography, which aims to create unbreakable encryption systems. Quantum key distribution, QKD, relies on the principle of quantum entanglement or superposition to create secure communication channels. Any attempt to intercept or measure the data would disturb the quantum state, immediately alerting the parties involved. Quantum cryptography is already being tested in secure communications, promising a future where data is nearly impossible to hack. In medicine, quantum sensors are pushing the boundaries of what we can detect and measure. Quantum magnetic resonance imaging, MRI, could achieve unprecedented detail, revealing molecular structures in real time and improving diagnostic accuracy. Quantum sensors can detect changes in temperature, magnetic fields, and electrical impulses with remarkable sensitivity, allowing for advancements in neuroscience, cardiac health, and other areas of medicine where precision is critical. Quantum teleportation represents another exciting, albeit experimental, frontier. While it doesn't involve physically transporting matter, quantum teleportation allows the transfer of quantum states across distances instantly using entangled particles. Quantum teleportation could one day lead to breakthroughs in communication networks, allowing data to be transmitted instantly, irrespective of distance. Though still in its infancy, the potential applications are enormous, possibly transforming how information is shared across the globe. As we stand on the threshold of the quantum age, these technologies promise to reshape industries and solve problems previously considered unsolvable. The power of quantum mechanics lies not just in its ability to describe the universe, but also in its potential to innovate. From powerful computation to unbreakable security and medical advances, the future of quantum technology holds the potential to redefine the limits of what humanity can achieve. Quantum ethics, navigating the moral implications of quantum advancements. With the advancements in quantum technology come profound ethical questions. Quantum mechanics has unlocked unprecedented capabilities, but as we move further into the quantum era, we must consider how to wield this power responsibly. From privacy concerns in quantum cryptography to potential shifts in social dynamics due to quantum computing, the ethical challenges of quantum technology will require thoughtful consideration to ensure that this knowledge benefits humanity equitably. Quantum cryptography promises unbreakable security through quantum key distribution, an attractive solution in a world where data privacy is increasingly under threat. However, this same level of encryption could present ethical dilemmas. Nations or organizations with access to advanced quantum cryptographic systems could hold impenetrable secrets, shielding information from public accountability, and potentially even hiding actions with global consequences. Balancing the right to privacy with the need for transparency will be essential as quantum encryption becomes more widespread. Quantum computing also raises questions around economic and social equity. The sheer power of quantum computers offers enormous benefits for industries like finance, healthcare, and artificial intelligence. But access to such technology may be limited to wealthy corporations and advanced nations. If only a small portion of the world has the ability to harness quantum computing for economic or medical breakthroughs, the technology could exacerbate existing global inequalities, widening the gap between technologically advanced societies and those lacking access. Another ethical consideration surrounds quantum technology's potential use in military applications. The ability to break traditional encryption could give militaries a powerful tool for espionage, disrupting communication systems and gaining strategic advantages. Similarly, the development of quantum radar and other surveillance systems could lead to unprecedented monitoring capabilities, eroding privacy rights on a massive scale. As quantum technology advances, creating international agreements or guidelines around its use in military and intelligence sectors will be essential to prevent it from sparking new forms of arms races or surveillance practices. Furthermore, quantum advancements raise questions about human agency and autonomy. Quantum computing could make artificial intelligence more powerful and sophisticated, potentially leading to machines capable of processing vast amounts of data about human behavior. Such insights might be used to predict and influence individual choices, posing ethical challenges around consent and free will. Should AI, empowered by quantum technology, be permitted to make critical decisions about healthcare, justice, or public policy? If so, who will hold these machines accountable? As we push the boundaries of quantum potential, the question of environmental impact also arises. Quantum computers require extremely low temperatures to function, leading to significant energy demands. Scaling up quantum computing could put pressure on global energy resources, pushing society to weigh the benefits of quantum advancements against the potential strain on environmental sustainability. Ultimately, navigating the ethical landscape of quantum technology will require cooperation across scientific, political, and social domains. Developing guidelines and regulations that address privacy, equitable access, and environmental sustainability will be crucial. The quantum era offers an extraordinary opportunity to expand humanity's capabilities, but it also places a profound responsibility on current and future generations to approach these advancements with integrity, foresight, and a commitment to ensuring that quantum technology serves the greater good. As we embark on this journey into the unknown, ethical stewardship will be the compass guiding our exploration, reminding us that scientific breakthroughs must be balanced with a deep respect for human dignity, freedom, and the preservation of our shared world. Quantum mysticism, blending science and spirituality. The peculiar and mind-bending principles of quantum mechanics have led to a natural overlap with spirituality, inspiring what is often called quantum mysticism. This movement blends scientific discoveries with spiritual ideas, exploring connections between quantum phenomena and age-old questions about the nature of consciousness, reality, and existence itself. While quantum mysticism has received both admiration and skepticism, it taps into the deep desire to understand the relationship between science and spirituality. At the heart of quantum mysticism lies the notion that quantum mechanics suggests a universe where all things are interconnected, transcending the limitations of space and time. The principle of quantum entanglement, where particles remain connected regardless of distance, resonates with concepts of universal oneness found in Eastern spiritual traditions. In Hinduism, for example, the concept of Brahman describes an ultimate, indivisible reality underlying all existence, akin to the idea of a quantum field that unifies particles and forces. This view suggests that the universe is more than the sum of its parts, embodying a holistic web of interconnected energies. Quantum mysticism also finds a parallel in the observer effect. In quantum mechanics, the presence of an observer seems to affect the behavior of particles, raising philosophical questions about the nature of consciousness. Does our awareness influence reality? Some spiritual thinkers suggest that consciousness is fundamental to the universe, aligning with concepts in Buddhism, where reality is seen as a construct shaped by perception. This blending of scientific and spiritual perspectives has led many to view consciousness not just as a feature of the brain, but as an essential part of the cosmos itself. The idea that our thoughts and intentions might influence reality on a quantum level has inspired practices like visualization and intention setting, where people believe that focusing on desired outcomes can influence events. Though not scientifically validated, such practices resonate with a common human intuition that our mental states and intentions might shape our lives in meaningful ways. However, it's important to recognize the caution advised by scientists regarding quantum mysticism. While quantum mechanics explores fundamental questions, applying its principles to explain consciousness or spirituality is speculative. Quantum phenomena operate on scales that differ drastically from human experience. And while parallels exist, direct connections between quantum mechanics and consciousness remain scientifically unproven. Despite these cautions, quantum mysticism continues to inspire a dialogue between science and spirituality, suggesting that reality may be a richer and more profound tapestry than science or spirituality alone can fully explain. By exploring quantum mysteries with open-minded curiosity, quantum mysticism offers a space for us to ponder questions of existence, unity, and the potential role of consciousness in the vast, interconnected universe. The legacy of quantum mechanics. Redefining reality. Quantum mechanics, with its paradoxes and mysteries, has redefined our understanding of reality. Since the early 20th century, its discoveries have not only transformed physics, but have also influenced countless other fields, from philosophy and psychology to technology and ethics. The legacy of quantum mechanics extends far beyond the laboratory, challenging humanity to see the universe through a lens of probabilities, interconnectedness, and infinite potential. It has forever shifted our view of what is possible and real. At the beginning of the quantum revolution, pioneers like Max Planck, Albert Einstein, Niels Bohr, and Werner Heisenberg were struggling to explain the unusual behavior of particles, leading to groundbreaking principles like the uncertainty principle and wave-particle duality. These principles defied the classical deterministic models of Newtonian physics and introduced a universe filled with uncertainties. In place of concrete predictions, scientists could now only calculate probabilities, indicating a reality where outcomes could never be known with complete certainty until observed. Quantum mechanics revealed that at a fundamental level, particles do not have fixed positions, paths, or even identities in the way we might expect. Instead, they exist as probability waves, shifting between states and locations in response to observation. This non-deterministic nature of particles introduced the concept of the observer's role in shaping reality, a radical departure from classical thinking. By incorporating the observer as an active participant, quantum mechanics opened the door to questions about consciousness, free will, and the nature of existence itself. As quantum theory matured, its practical applications began to reshape the modern world. Technologies like semiconductors, lasers, magnetic resonance imaging, MRI, and quantum computers all owe their existence to our understanding of quantum mechanics. These advancements have revolutionized fields as diverse as medicine, computing, and telecommunications, creating a world that would have been unrecognizable a century ago. Quantum mechanics' legacy in technology demonstrates the power of understanding reality on its smallest scales, as even the most theoretical aspects of quantum theory have led to practical, life-changing inventions. But beyond technology, quantum mechanics has influenced how we perceive reality and our place within it. Philosophers have used quantum theory to question the nature of objectivity and the limitations of human knowledge. The idea that particles exist in superposition until observed has inspired new ways of thinking about personal experience, perception, and even social and ethical responsibility. If our observation shapes reality, are we not, in some sense, co-creators of the universe? This understanding leads to one of quantum mechanics' most profound legacies: the challenge to our assumptions. Quantum mechanics teaches us to embrace uncertainty, to look beyond fixed categories, and to remain open to complexity. In a quantum world, reality is not a static, unchangeable entity, but a fluid interplay of possibilities, a dance of probabilities that holds mystery at its core. In reshaping science, technology, and thought, quantum mechanics has left humanity with a legacy of curiosity, wonder, and humility. It reveals a universe that resists easy answers, urging us to explore the unknown with respect for the depths we have yet to understand. The legacy of quantum mechanics is not simply a set of scientific laws. It is an invitation to question, to explore, and to continually redefine what we believe is possible in the fabric of reality. The final mystery. Is reality knowable? At the end of our journey through quantum mechanics, we face a profound question. Is reality ultimately knowable? Quantum mechanics has offered glimpses into the universe's smallest scales and deepest mysteries, yet each answer often leads to more questions, suggesting that reality itself may be boundless, forever just beyond the grasp of human understanding. Quantum mechanics has revealed that certainty, as we once knew it, is a limitation rather than a truth. The uncertainty principle, wave-particle duality, and entanglement challenge our desire for predictability and fixed definitions, replacing them with a universe of probabilities, shifting states, and interconnected particles. These discoveries suggest that perhaps reality is not a puzzle with a single solution, but a dynamic, evolving web of possibilities where absolute knowledge remains elusive. For some scientists, reality's unknowability is a natural boundary. Just as there are limits to our observation, restricted by light speed or the Planck length, there may be inherent limits to our understanding of existence. In this view, the human mind, evolved to interpret survival-based reality, may simply lack the tools to fully comprehend a universe governed by quantum probabilities. This view is a reminder of our own smallness within a cosmos that defies our intuition. Yet, for others, the limits of understanding only inspire curiosity and exploration. The mysteries of quantum mechanics have often given rise to surprising breakthroughs, even when scientists ventured into realms that seemed nonsensical or paradoxical. What might seem unknowable today could be illuminated in future eras, sparking the hope that reality is not a finite concept, but a boundless frontier of knowledge. This final mystery of reality's knowability touches on philosophical questions that have endured for centuries. Is the universe a fixed structure waiting to be discovered? Or is it a construct shaped by our interaction with it? Quantum mechanics hints that reality may be participatory, something we engage with rather than observe passively. If so, our understanding of reality may be inseparable from the ways we perceive, measure, and think about it, a truth that continues to evolve with each discovery. In the end, whether or not reality is knowable, quantum mechanics has revealed a universe more wondrous, complex, and interconnected than we could have ever imagined. It invites us to see mystery not as a barrier, but as an essential quality of existence itself, something that adds depth to our pursuit of knowledge. The final mystery of reality reminds us that the search for understanding is a journey without end, a journey where each new question brings us closer to, and yet infinitely farther from, the ultimate nature of existence.